some derivatives are harder to find than others. And some derivatives, talking about the derivative of y with respect to x, what we normally typically find. For example, x cubed plus y cubed equals 15xy. This is an equation here. First thing we note right off the bat is it's a lot different than y equals x squared plus 2x minus 15. A regular function, because you don't have y on the side by itself. It's not in the function form. And matter of fact, this one will be hard to put into y equals form. And however, the graph of this, it's called the folium of Descartes. Let me just draw it up here. It looks like this, or something similar to that. I draw it up here because doesn't it make sense here to think about the derivative of y with respect to x, because we know the derivative of y with respect to x is what? For the graph, it's what? Slope of tangent lines? Don't these have tangent, doesn't this graph have tangent line? And wouldn't those tangent lines have a slope? Yes, they would. So it makes sense that we should be able to come up with a derivative of y with respect to x. Now, we know how to do these, just power rule and quotient rule if we have to, and all those rules. This, on the other hand, it's in a whole different format than what we're used to. And so that's why we talk about another type of differentiation, which is implicit differentiation, because the word here, implicit, this is a function, and what that means is I've got y explicitly in terms of x. It's explicitly defined in terms of x. I may be able to find what y is in terms of x is here, but for this one in particular it would be difficult, and for some of them it may be just impossible to find. So what I'm saying is I can't explicitly solve for y here, or maybe it's difficult. We didn't call it, but so we can't do our explicit differentiation like we did over here to find the derivative. That's why we use this implicit, what's called implicit differentiation. It's differentiation, not necessarily through the back door, but a different way, okay? We're going to do it a different way, solve for the derivative, find the derivative, using what's known as implicit differentiation. Okay, so that's my little intro there to why we need this. Now, to get to that, let's take it kind of a step-by-step process. So we're not going to be able to solve explicitly for y over there, to find the dy over dx, the y prime, whatever you want to call it. But let's start with this. All right, so let's think about, if I said differentiate y to the 8th with respect to x. Here's what we've got to consider. So I'm differentiating with a y expression with respect to x. And so here, what the assumption is y is something in terms of x. Okay, it may not be this function, but it's something in terms of x to the 8th power. So I've got y, whatever it is, I don't know what it is, and it's to the 8th power. Okay, so think of it in those terms here. All right, and so here's just a little notation. All right, so another way to state this is what's the ddx of y to the 8th? I want to differentiate this with respect to x, y to the 8th. Well, one part of this is very easy. It's not really that hard, but you just got the power rule there, don't we? We got a y to the 8th power. I better use a power rule on that. So I've got 8y to the 7th, right? All right, so now, here's what else I've got. My phone off. All right, so we got 8y to the 7th. Now there's more to it though. Remember what we said, this y is something to the x power. Something in terms of x. So in other words, I've got something on the inside here. You see what I'm saying? The y, I don't know what it is. Phone's going crazy. I don't know what it is, what the y is, but I've got something, the y on the inside. So isn't that kind of a chain rule? So what I have to think of is, well, what would that be? What would the derivative of the inside be? Well, I don't know what the inside is, and so here's how I write it. I'm going to write that inside derivative, if you will, as dy over dx. Because I don't know what it is, but I know I need to do the derivative of it with respect to x. So it's kind of a chain rule. Now, do we have to think through all that each time? No. Because here's what it amounts to. Whenever I do the derivative with respect to x of a y that is thought to be something in terms of x, not only do I have to do the derivative, what appears, power rule, whatever it is, quotient rule, chain rule, but I've also got to include this dy over dx expression. That's what it amounts to. It's adding that expression to whatever the derivative is. Okay? So in other words, if I do the d dx of 4y to the 6th, what do you got there? Well, just the 4y to the 6th power, I've got 24y to the 5th. So, that's the power rule, but I'm doing the derivative with respect to x of a y, so I've got to add this dy over dx. All right? So far, so good. Now, here's the thing. I will still have some expressions that have just x in them. So if I said, what's the d dx of x cubed plus 5x plus 4? That's the derivative with respect to x, but all these are x's. So do I need the dy over dx with those? No. Because these are x's, I only need the dy over dx with the y's, the y stuff, okay? So this is just still straight up derivative. I'm doing the derivative with respect to x of an x expression. So that's 3x squared plus 5. That's so I don't need, no dy dx needed there. Okay? Now, here's what can happen as well. All right, so what about the d dx of 8x cubed y to the 4th? Derivative with respect to x of that. Well, same rules apply as we've always had. We got product rule, we got chain rule, power rule, quotient rule, just to name a few there. I guess that's about it. I've got a product rule there, don't I? Product rule. And you don't necessarily have to write it all out like this, but let me just show you out here what this is going to mean. So I've got to use the product rule in this. So I need to do the derivative with respect to x of 8x cubed times just the y to the 4th And then alternate that, do the 8x cubed times the derivative with respect to x of the y to the fourth. Like I said, you don't have to write it out each time like that, but that's what I've got to do, all right? Now, the derivative with respect to x of 8x cubed, well, it's already an x, so it's just straight up power rule there, 24, one less power, and then the y to the fourth, right? But then over here, I've got 8x cubed. The derivative with respect to x of y to the fourth, well, that's power rule for y cubed, but what else do I need with it? dy over dx. And again, why do I need it here and not here? Well, it's because I'm doing the derivative with respect to x of a y here, or a y expression. And whenever you do the derivative with respect to x of a y expression, you've got to add this dy over dx expression. When you do the derivative with respect to x of just x, you don't need it. So that's why it's here and it's not over here. And of course, multiply, clean that up. That'll be 32 x cubed y cubed dy over dx. All right? Question? Any question? Okay, well, what are we talking about that for? Well, let's start with this one. X squared plus y squared equals 25. This will be our first one that we're going to use, implicit differentiation, to find dy over dx. And notice again, I'm using the Leibniz notation. Instead of the y prime, it's just makes it different, I guess, so to speak. I mean, we could use y prime, but there's a reason also, there's another reason for using dy over dx for later on, what we do later on. So, all right. So we're going to find the derivative, whatever you want to call it, dy over dx. So here's step one. Step one is take the d dx of both sides. For implicit differentiation, take the d dx of both sides. Like I said, I'm writing all the steps out here. We can condense some, combine some as we get more accustomed to this. But it's just taking the d dx of both sides. Now this side, well, this side's pretty nice because it's just adding. And so it just amounts to the d dx of x squared plus the d dx of y squared. Because it's just adding, there's no special rule there. Just straight up do the derivative of each with respect to x. Now we can go ahead and take care of this one. What about this side? Well, it's the derivative of constant. That doesn't change. That's still 0. But what about these two? Well, the derivative with respect to x of x squared is just 2x. And since I'm doing with respect to x, and it's just an x expression, I don't need the dy over dx there. It's just straight up derivative, powerful. Over here, on the other hand, the derivative with respect to x of y squared is 2y. But I'm doing the derivative with respect to x of the y expression, so I need the dy over dx on that. See the difference of those two? Okay. So that's step one. Take d dx of both sides. Step two is then solve for dy over dx. It's really a two-step process. Sometimes it takes longer than others. These can get quite lengthy, but not generally too bad. So let me move over here since I'm putting a little space there. Just copying what I've got. 2y plus 2x plus 2y dy over dx equals 0. So I want to solve, it's like solving an equation, except in this case I'm going to solve it for dy over dx. Well, to solve for dy over dx, right? I need to move this term to the other side, so I'm going to subtract 2x from both sides. So I have 2y, dy over dx, and then subtract it, so it'd be minus 2x to that side. Now, that 2y is times the dy over dx, and so let's divide the 2y off. So we have dy over dx equals, and of course the 2's cancel, so it's minus x over y. Ta-da. Okay. Isn't that what we're trying to find, the derivative? Once you get it solved for dy over dx, that's your derivative. Now the difference between this derivative and the previous derivatives, what we encountered was, you notice something different about this? I've got x and y involved in the derivative. That's okay, because if we were trying to find a specific value slope of a specific tangent line, all we have to do is plug in the x value and the y value instead of just having to plug in the x value. Now we'll probably have to plug in an x and a y value in. That's doable, okay? Okay? Now, this particular example, I chose this one because we can actually see that using our old techniques, we can actually see this is the derivative using our old techniques, because here's what I can do for x squared plus y squared. I can't do it for all of these ones I do implicit on, but I can actually do this one. Let's find the derivative dy over dx or y prime by first solving explicitly for y. So in other words, do it the old way. So I want to take x squared plus y squared and solve that explicitly for y, because I can do that here. I can't do it on some others. That first one I gave you, we couldn't do this for that one, but this one we can, because if I solve this one explicitly for y, so I would subtract x squared from both sides, and that gives me y squared equals 25 minus x squared. Trying to solve for y, so y, I would do the square root, right? Y equals the square root of 25 minus x squared, and technically it's plus or minus. You have to do the plus or minus to get both sides, because does anybody recognize what I've got here, graph-wise? Isn't that a circle? Radius 5. And so the top half would be the positive square root of 25 minus x squared, and the bottom half is minus square root of 25 over x squared. But that's, so that part's y equals 25 minus x squared, radius 5, and the bottom half is y is minus the square root. But I digress. I don't really have to know that in particular, but anyway. All right, so our goal is to find the derivative dy over dx or y prime. So y prime or dy over dx, either way. How am I going to do it if I do it this way? It's chain rule, isn't it? Write that as 25 minus x squared to the 1/2 power. So it'd be plus or minus, bring down the power, new power, so inside stays the same. New power is minus 1/2, subtract 1. But then what's it times? Derivative of the inside. Derivative of the inside will be minus 2x. That's my derivative that way. Now, we're trying to compare to make sure these two are the same. That looks a whole lot different than this. But let me just clean this up a little bit. All right. So let's say I do this. So that would be in the denominator. That would be, so I'd have, oh, the 2's cancel. So I've got a 2 and then a minus 2 there. So, but that would be in the denominator as the square root of 25 minus x squared, right? Because it's minus 1/2 power of the square root of 25 minus x squared in the denominator. And then on top, well, I got 1 and then minus x. And let's write, just to make it ever so clear, let's write that plus or minus down here. Because what is this? So I just wrote the plus or minus with that. What is this right here? N to the 10th. What is that right there? Plus or minus square root 25 minus x squared. Isn't that y? No. It works. It works. You get the same result either way we go. Now, I guess we could debate here which one looks easier. The final answer, this one looks a whole lot easier, doesn't it? Whether it's easier or not process, but the point is, we can do it either way on this one, but some of them we won't be able to do both ways. All right? So we'll do some more here.